Okay, أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. الحمد لله والصلاة والسلام على رسول الله. This is a special video review tutorial for test 2. It's meant to be a revision for chapters 24, 25, and 26. Remember, please underline the word revision. So I'm going very quickly over the concepts, and I'm reviewing some of the expressions and the relationship between the two, the different parameters and the different ideas and different concepts that we studied or discussed in class. So this is meant to be a review, but you still have to go back and study the details that we took in class, because that's very, very, very important. Okay, so let's start. In the first chapter, chapter 24, which is in capacitors and dielectrics, what we've done, we started by introducing something, a new parameter or a new property of material. A new parameter, in fact, is called the capacitance, and a new device, which is called an electric device, is called the capacitor. And the capacitor, as you recall, is nothing more than a device that is designed in such a way that we want to store electric energy in it to use it later on. And the simplest example for that is the flashlight in your camera. So you charge the capacitor, or you charge the capacitor, and then when you click the flash, that's a discharging the capacitor. The flashlight that you see very short, that's the discharging the capacitor. So we use to define capacitors and the capacitance of a capacitor. We first looked at the types of capacitors that we use. So we have the parallel plate capacitor, we have the spherical capacitor, and then we have the cylindrical capacitor. In each one of them, we have a positive plate and a negative plate. The charge on both plates is, the magnitude of the charge on both plates is the same, and there is a gap between the two plates, which are, if you take any two opposite points and you go around the capacitor, the distance between these two opposite points, or next to each other or against each other, is the same throughout, whether in the parallel plate capacitor, or whether in the cylindrical, or whether in the spherical plate capacitor. We've looked at the three different types, and the capacitance of a capacitor is determined by looking at the relationship between Q and V. So when you look at the relationship between Q and the voltage drop, which is linear, the constant of linearity, or the slope of this graph, Q versus V, which is linearly proportional to V, the constant or the constant of proportionality, or the slope, is equal to C, some constant value, which is called the capacitance of the capacitor. And it's a purely, if you remember, we said that it's purely geometric value, so it depends on, or purely it depends on the geometry, and also depends on the space or the medium in between the two plates. So the three types of capacitors, as I mentioned, you have the first of all, the famous parallel plate capacitor, where you have two plates opposite to each other with surface area A and the separation, or the gap D, and then the capacitance is defined as epsilon A over D. So as A increases, C increases, and as D increases, C decreases. And then you have the cylindrical plate capacitor, which has a length L of the cylinder, and A is the inner radius and B is the outer radius. Again, depends on geometry, and the medium, which in this case we choose vacuum. Okay, and the spherical plate capacitor, so you have two spheres, concentric spheres, and again the cylinders here are concentric, and the inner radius A and the outer radius B. And again, the capacitance is in terms of the geometry, A and B, and the space in between them. All right, so the second thing that we looked at, okay, we know that the capacitance is used for storing energy, electrostatic energy. So one interest, main interest for us, is how can we increase the capability of storing energy or decrease the capability of the capacitor to store energy. One way of doing that is by connecting the capacitors, a group of capacitors, in parallel. And as you can see, if you connect them in parallel, you increase its capacity. That means you increase the amount of energy that can be stored in the capacitor, or you can reduce it by connecting them in parallel. And we looked at how we derived these two formulas. Another thing we looked at, or we calculated, or we derived, is the potential energy stored in a capacitor, which again is determined from the area under the curve QV. So QV, if you look at the area under the QV and you looked at its dimensions, you find the dimensions of it is energy, joules. And we looked at that in class very well. So the potential energy is equal to that. And then using the fact that Q is equal to CV, they can have two other formula. And we looked at the energy density, which is simply the energy stored in the capacitor per unit area. And that we found that is related to the electric field square inside the capacitor. So this is one way of changing the capacitor, reducing, increasing, the capacitance of a capacitor. Another way is by introducing a dielectric material. Dielectric materials are those insulators that when you insert them inside the electric field becomes, the electric field becomes less, is reduced, and therefore the capacitance of the capacitor is increased. So introducing a dielectric material will increase the capacitance and will reduce the electric field by reducing the electric field inside that capacitor. Okay. So let's look at some examples, and the first example we're going to look at is the famous example where we have some circuit, a combination of capacitors. They're connected to some battery, which is 15 volt, and the question will be to find the charge on each capacitor and the voltage drop across each capacitor. And the way to do that, and I think we mentioned that in class, or we did a lot of examples in class, is first by we're going this way, or by first looking at the equivalent capacitance, equivalent capacitance for the for the combination. So the first thing I do, I want to get these two first. Okay, so these are connected in parallel, and so I simply add them. That will give me 10 plus 20 is 30, and then I combine these three, which are now this with that, so that's in parallel, in series, and then all of these together. And as you can see, when you connect everything together, you get the equivalent capacitor for the whole thing is 5 microfarads. So what I have now, I have a circuit. If I take the pen, I have a circuit that is something like this. Connected to equivalent capacitor, right? And from here, from this circuit, which is now 5, this is 5, okay? And from here, and V is equal to 15. From here, I can find the total charge, in the circuit, which I found to be is equal to simply 15 times 5, which is 75. Now, wait. There are two things that I have to keep in mind here. One of them is the fact that I have to know that when capacitors are connected in parallel, the voltage across the two capacitors or the three capacitors that are connected in parallel is the same. When the capacitors are connected in series, the charge on all capacitors is the same. So armed with this condition, that means what? If I know the total here, this is connected with these two, that means what? That means this charge is the same as this charge, is the same as the charge of the two capacitors here. So that means my charge of capacitor 4 is simply 75, and my charge of capacitor 1 is equal to 75, and from here I can get the voltage drop across these two capacitors using Q is equal to CV. Now the other thing I notice, or I know, is the fact that once I do that, I know that the voltage, the total voltage, will be equal to this voltage plus this, because they are connected in series with these two together. So what does that mean? That means the voltage across these 2, 3, from here I can calculate the voltage across these two guys, which is equal to 2.5. So the voltage here is 2.5 and the voltage here is 2.5, and then my problem is solved. Q2 is equal to, Q2 I can calculate it from Q is equal to CV, and Q3 I can calculate it from Q is equal to CV, and there you go. So anyways, the second question that I want to look at, so this is the first way of changing the capacitance by simply connecting in parallel or connecting in series. The other way, or the second way, is by simply looking at if you have you insert a dielectric between these two capacitors. In such case, so for example, in something like this, where I have a capacitor and I inserted two dielectric materials filling the gap in between it, so there is no space here really. This is equivalent. This is equivalent to something like this. So these two guys can be. It's exactly the same thing. So what's the only thing that is different is now the area is half, because if this is the area, now the area is half, but the gap or the distance between the two places is the same. Since it's parallel, so C equivalent is equal to C1 plus C2. And remember, when you insert a dielectric, you simply multiply by kappa. So epsilon over, this is A. So the area is half of the area, right? And the area here is half of the area, okay? And then when you add, you take everything out, you see the equivalent capacitance is equal to simply the capacitance multiplied by half the capacitance multiplied by the sum of the two dielectrics or the dielectric constants. Okay, now let's look at the other one, another example where now I have a dielectric the capacitor, a parallel plate capacitor, and I inserted the metal. Remember, the dielectric materials are insulators. So if I insert a metal which has the separation between the capacitor, the plates is D, and the thickness of the metal is A. So that means what? That means this is really something like this. So it becomes simply, because remember, D minus A, and you have two of them. So D minus A divided by 2 will give you this, and D minus A divided by 2 give you this. But remember the metal. The metal can be just considered as a wire because it's a conductor, right? So now I have two capacitors that have dimensions A as a surface area and a gap D minus A divided by 2, and they are connected in series. So when I do the equivalent capacitance, if I wanted to calculate the equivalent capacitance, so 1 over C equivalent is equal to 1 over C1 plus 1 over C2. And remember, C is equal to epsilon A over D, right? So this becomes, because remember, C is equal to epsilon A divided by D. In this case, D minus A divided by A. So this, it comes up, and it's simply, you can see the math very easily. And then if you look here, everything is the same, right? So if you pull this, then it will become half plus half is equal to 1. Okay, or 1 plus 1 is equal to 2 divided by 2 is equal to 1. And then this is my C equivalent is equal to that. So if you do the math, it will be very easy to see how you can get this one. Now the question is, he gave you two conditions. What happens when A goes to 0? When A goes to 0, so the metal is not there. So I should get the capacitance equal to epsilon A divided by T. Sure enough, divided by D. Sure enough, if A is equal to 0, then epsilon A divided by D. Okay, what happens if A goes to D? If A goes to D, that means the metal is almost filling the whole space. That means D goes to 0. If D goes to 0, if A goes to D, so that D minus D is equal to 0. So that means something over 0, which is infinity. And we saw that before, because remember the capacitance, if this goes to 0, the capacitance goes to infinity by definition. And I think we explained this in class very well. All right. Another example which is taken from the last quiz, and he said, okay, what happens to the potential energy when you double the dimensions of the capacitor? That means what? That means you double both the area A and the separation D. Now, if we look at the definition, so this will be the C is defined as epsilon A divided by D. If you double A, so this becomes 2A, and if you double D, it becomes 2D. So the 2's will cancel and nothing happens. So the answer here stays unchanged. Now be careful. What happens if you double A and you do not, and D stays the same? Then the potential energy is doubled. What happens if you double D and this stays the same? Then the energy is half, and so forth. So be careful with that. Now, another example, if you have an air-filled, remember A has a cap of equal to 1. Has a capacitance of 50 picofarads. Remember, the capacitance is measured in farads. Most of the practical capacitors that we use in the lab are measured in picofarads. If each of its plates has an area of that in meters, meter square, what's the separation? And now I can, and if the region is now filled with the dielectric material, what's there? What's the new capacitance? Now, this is easy. So C0, the initial capacitance, or the original capacitance, epsilon naught A divided by L. I'm given A, and I'm given the C. So from here, I can find D. No, actually, he gave me the area. He wants the separation, so I can find D very easily. Now the other thing, okay, what happens when it's filled by 5.6? So from here, the separation is L. So all I need to do is that 50, that's my C0, and then multiply it by 5.6, and voila, then done. Okay, another problem, but except it's a little bit long problem. So I have here a parallel plate capacitor with plates equal to, let me just take the pen here. This is the area in centimeters square, and an air-filled separation of 3 millimeters. So I already have a problem here that I have to make sure that I sort this out. And the best thing is to use meters, and the volt is that. They are disconnected. So this is the first connected, and they are disconnected from the battery pulled without discharge. So that whatever charge you put when you connect them to the battery is not going to be discharged. So you do not click anything. To a separation. So now, after you charge them, you pull the separation. So you change D from 3 to 8 millimeters. Neglecting fringing means what? Means that you're away from the edges. So you're in the uniform electric field region. Find the potential difference between the plates, the initial stored energy, the final stored energy, and the work required to separate the plates. Because remember, when they are attached to each other or attracting each other, if you want to pull them apart, you have to do some work. Okay, so let's first of all calculate the initial capacitance. I've changed, remember the area, I changed the centimeter to meter, and I changed the millimeter to meter, and I get the initial capacitance is equal to 2.5 picofarads. And from here, I can calculate the Q, the charge. It's simply CV, because V is equal to 6 and C is this. So from here I can find the charge on the capacitor. Remember, this is uncharged, so this will stay constant. After that, I want to calculate the final capacitance. Now, because I pulled it from 3, I pulled it to 8 millimeters, and from here I can calculate that 9.4, which is the new capacitance. Because remember, this depends on geometry. It has nothing to do with the battery. It has nothing to do with the charge. From here, I can calculate the new voltage, because Q is the same and C changed. So now my voltage is 16. So voltage goes from 6 to 16 volts. This allows me to calculate the initial potential energy, which is simply, I'm going to use half CV squared. C is given, and V for the first one is 6. For the initial one is 6 volts. And I'm going to calculate the final potential energy, which have V final, which is 16, and C final, which is this one. So that will give me, this will give me 4.5 times 10 to the minus 11 joules, and this will give me 1.2 times 10 to the power of minus 10 joules. Now, to calculate the work done is simply, remember the definition, work is equal to the change in potential energy. All right, and that's my, so the amount of work needed to separate the plates is equal to, or to pull the plates apart to 8 millimeters is that much joules. All right, okay, next. Let's go to chapter 25. And in chapter 25, we looked at current and resistance. Now, current is defined as you remember, if you have a number charges n, they're flowing in some volume. I first have to calculate the n, which is the small n, which is the number of charges per unit volume. And remember, Q, the definition of the current, is simply Q over T, or the rate flow of charges. Rate meaning the charges per unit volume, or as they flow across. So the current I can also be, and we saw that in class in detail, can also be, let me just click all of them and then I get my pen. Okay, so the current is defined as this, okay, and delta x over delta t is defined as something called the drift velocity. And the drift velocity is the velocity by which the electrons are flowing across some region, across some specific area. And now this is not the zigzag velocity, because the zigzag velocity, remember the electrons go like this, so this is not the zigzag velocity. This is the velocity as the electrons move across the drifting along the wire. And if you divide by A, if you divide I by A, then you get something called it's something called the current density. So V drift velocity is I divided by N divided by A divided by Q, and this I divided by A is called the current velocity, and it's a vector. Now N is defined as the number of charge carriers in the volume V, that's small n. So whatever the volume is, of which the volume is simply the area multiplied by delta x, and that's my volume here, right? And again, I can calculate the drift velocity. Again, the three important formula. I is defined, or the current is defined, the rate flow of charges, and the current density is I over A, and the drift velocity is J over NQ. Remember, this Q is the charge, and most of the time we'll be using electrons, so Q will be simply E. Another thing that we talked about is the the power dissipated across a wire or across a resistor is simply IV, or I can use Ohm's law, V is equal to IR, and from there I can get the power is I square R, or V square over R. Okay, the second thing that we need to look at, or we need to review, is the resistance. Okay, I'm going to just click everything, and then I need get my pen so that I'll scribble. First of all, we looked at resistance. Resistance is defined again in terms of geometry, and I say again because I'm referring to the capacitor, or the capacitance is also a geometric thing. It depends on L, depends on A, and it depends on something called the resistivity, which is a property of the material. So geometry plus property of material. Or I can write the resistivity as R A over L. And the conductivity is simply 1 over the resistivity, and that's what that is. All right, let me just show you, come on, let me just show you a video, not a video, but a simulation of how does the resistance depends on rho and L. This is from FET, which is the physics net, and it's free from the University of Colorado. And it's very nice simulations of all these formulas, and you should visit it if you want, if you have time and you want to look at this. So how does R depend on these three, the geometry and the property of the material? If I reduce the resistivity, okay, and if you look here, the resistivity means that there are less obstacles for the current to pass through. So that means what? That means the resistance becomes less and less and less. Right, less obstacles, I mean less collisions, less number of collisions in the wire. Okay, so as you increase rho, R increases, and length, as you increase length, again, because you're increasing the number of or the probability, the collision probability. Okay, so that's, again, it's going to increase it, it will increase, decrease it, it will decrease. Now here, as you can see, because there is more space, you're creating more space in between the two particles inside the wire, or the charges inside the wire, and then that means what? That means as you increase A, the cross-sectional area, R becomes less, and as you increase it, decrease it, R becomes big. All right. Let's go back to our okay. So we did that. Now it's time. The other thing that he did not look at is the temperature. The resistivity depends on A and L. And if you look at the resistance depends on the dimensions and the resistivity, and also depends on the temperature. This is through the resistivity, because the resistivity depends on the temperature of the material using this formula, where rho 0 is the resistivity at some reference temperature, usually room temperature, and alpha is a temperature coefficient that has tables for each material, and T0 is the reference temperature, and as I said, usually this is room temperature. If I have A and L as the same, and I use this equation here, or this actually I use this equation here, so then I have R A over L and R0 A over L. So the A over L cancels from both sides, and I get the formula or the dependence of the resistance as a function of temperature. And as you can see here, as the temperature increases, the resistance increases. All right, and because this is constant, and this is true for when alpha is positive. But if alpha is negative, then we get the other. But for most materials, alpha is positive. Okay, let's look at this question here. I have a copper wire that has a diameter of 2 millimeters. Again, the issue of the units. Be careful with this. Yeah. So diameter, that means I have to divide by 2 to get the radius, and it carries a current, that much current, very, very small current. If the number of charges per unit carrier is that's small n, okay, and this is I, and since I have the diameter, I can get the area, okay. If the current is uniform, so the current does not change through the wire, calculate the current density. Current density is simply I over area. I have I, and I have the area, so from there I can calculate that. And the drift velocity, we know how to calculate the drift velocity from the equation the previous. So first of all, I calculate the current density with simply I over A, and diameter divided by 2. If you do all the units correctly, you should get this answer. And remember what the drift velocity looks like, or the formula for that. So if I want the drift velocity is I over that, and since I know what this, I've calculated that already, right? J, so it will be J over N. Q, remember Q is the charge of electron, okay? And then we find this very, very, very small drift velocity, which we said in class that it is supposed to be small. All right. Now let's look at another example where I have a wire of length 1 meter. Again, the issue of the units carries a 4 amp current and is connected to 2 batteries. What's the conductivity of the wire? Remember, the conductivity is 1 over the resistivity. Conductivity sigma is equal to 1 over the resistivity. Resistivity, how resistive or how resistance, the resistance of the wire, and the conductivity is related to the how good of a conductor the wire is. So these are all, both of them are properties of the electrical properties of materials. So if the conductivity is high, that means good conducting material. If the resistivity is very high, that means it's a bad conducting material or insulating material. Okay, so let's see how we're going to solve this. First of all, I go back to my formula, and he did not give me R, but he gave me both the current and the voltage. So using V is equal to IR, which I did not mention, but everybody should know, Ohm's law. V is equal to I multiplied by R. So that means R is equal to V over I, and then I can again do one more thing. So rho is equal to cross multiply VA divided by L, and from here I can reverse it, okay, and then it will be IL over VA to get the conductivity, and put in the numbers and you get that number for the conductivity. Okay, another example, a common flashlight that has rated at, and this is something that I should, rated at, okay, so rated at, that means the flow of electrons in the material is that, which is the current. The flow of the material, the charges in that material is at this, so that means the current. And the voltage, Okay, and now if the resistance, if the resistance of the bulb filament at room temperature, which is 20, is equal to that. So at room temperature, the resistance is, so this is my R0, okay, and this is my T, this is my T0, the reference temperature, which we said usually room temperature. What is the temperature of the filament of the bulb is on? So now this is what he told me what the filament is operating at. That means the first thing I wanted to do is calculate the resistance, because he gave me the current, he gave me the voltage, V is equal to IR, so R is equal to V over I, and this will be my R, and this will be my I0. Going back to this equation for the which relates the resistance, the resistivity to the temperature, and using R and using the definition for the resistivity in terms of R, and the A and L are not changing, so that means it gives me this equation. So R, A over L from both sides will cancel, and then I have R0, so I multiply it here, R0, and alpha R0 here, and alpha is a constant which for tungsten I can get it from tables, and if I do that I just need to take this to the other side, so this will be R minus R0, and then divide by this, and then I take T0 to the other side, so it becomes plus, and that will give me T. Okay, so T will be all of this plus T0, which is 20. If I put in the numbers, I notice that the temperature is 1750. So that means what? That means in order to increase the resistance, or the cause of increasing the resistance from 1 to 2.9, 1.1 to 2.9, the temperature of the resistor has increased from 20 to 1751. Okay, so it gives you the relationship between as the resistance increases, so does the temperature, or as the temperature increases, the resistance of the wire increases. All right, next. Very interesting question, okay, because I was surprised that some of you did not know how to do this. But anyway, so the figure here shows, it's a multiple choice question in the last quiz. The figure shows that a steady current, electric current passing through a wire, and then narrow regions. So I have three regions, region A, region B, and region C. So the only difference between them is that in here, the cross-sectional area is smaller. Right. Now, if you look at it, and he wants to know what happens to the drift velocity. So he wants to look at VD. Now, as you can see, I stays the same, N stays the same, Q stays the same. The only thing that changes is A. Now, when A becomes less, that means I becomes bigger or increases. So what does that mean? That means in this region, in going from A to B, the velocity increases, and in going from B to C, the velocity decreases. And if you look, it's this, the drift velocity increases from A to B, and decreases from B to C. Okay, so that's the how to solve or how to look at this question. Next question, you have a resistor connected to a 3-volt battery, and the energy dissipated is equal to that much. So remember, the energy dissipated, which is the power. The power is W, or the energy over time. It gives is measured in watt. And when the same resistor is connected to 1.5 volt battery, what would be the rate of the at which the energy is dissipated? So he wants the power, the new power. Now, using this equation, P is equal to I squared R, and or is not V squared over R. From here, since he gave me the volts, I can get R, because he gave me the power, he gave me the volts. I can get R, which is the resistor, which is a constant. Always you want to find something which is constant, does not change. So this is the resistor, the value of the resistor. And then now I can use it when he changed the voltage. P nu is equal to V squared over R, because this is going to stay the same. Okay, and then the new power or dissipation, power dissipation is equal to that, 0.135. So as you can see, the power drop from 0.54 to 0.135 by when simply decreasing the voltage. So if you decrease the voltage, the power is also decreased. All right. Now, chapter 26. chapter 26 is all about looking at how simple DC circuits, and in here we will only look at circuits that have resistors and power supply. Yeah. Now the objective here is that if you're given some circuit like this, the question will be, or the objective is to find the value of the current in each part of, or in each element, through each element of the circuit. So you want the current through this, and the current passing through here, the current passing through here, the current passing through each element of the circuit. That's the objective. And the way to do that by using something called Kirchhoff's rules. And Kirchhoff's rule says that there are two of them. The first one says that the voltage across a closed loop is equal to 0. What's a closed loop? Something like this. That's a closed loop. And where you start from here, you go through a battery, voltage increase, voltage drop, voltage increase, and then you come back. And the junction rule, in which says that the sum of the currents in any junction point where more than two or more currents meet. So I have 1, 2, 3. So more than two currents meet. And what it says that the sum of the currents in that junction is equal to 0. For example, here I1, actually I1 plus I2 plus I3 is equal to 0. If one of them is out, that will be negative. Another way of writing this, I just wanted to write the sum of currents into the junction is equal to the sum of the currents out of the junction, which I like this better. It's easier to see so that you don't have to worry about the negative sign and the positive sign. Okay, so these are the two Kirchhoff's rules, which are used to find the current through any loop or through any element of the circuit, the DC circuit. We can also have the RC circuit, but we did not have time to do it, at least for test 2. All right, in order to do this, we have to keep in mind the sign convention. The sign convention we have is that if for resistors, if you're going against the current, if your motion is going against the current, that is a voltage increase. If you're going with the current, if your motion is along the direction of the current, that's a voltage drop. So this is for resistors. For batteries or sources, if you go from low potential to high potential, that's an increase. And this is easily can be seen. High minus low is positive. And if you're going from high potential to low potential, that's a voltage drop. Okay, and I will explain this very well in the class, and you should not have any problem. So this is the concept of voltage drop and voltage gain across a battery source or a resistor. All right, let's take two examples. One example we'll take in detail, and another one will be I'll just give you the answers, and I just set it up for you. Okay, so if you look at this, what is the objective here? The objective here, the question will be, for the circuit shown, find the current in each resistor. So he wants to find I1, I2, and I3. And he could ask you to find the voltage drop across here, the power dissipated across here, and the voltage drop, for example, between these 2 points, and so forth. But in order to do that, you must find the currents. And that's always the objective. The objective is to find the currents through each resistor. If you have V, if you have I and R, you can calculate V at any point. So how do we do this? I'll show you here a step-by-step solution or systematic solution, so that if you follow it, chances are at least you'll do the physics right. Okay, step number 1, identify the loops. So here I have identified, this is my loop. So I start from here, for example, and I go all the way around. I have a voltage increase, a voltage drop or increase, and then I come back to that's a closed loop number 1. Closed loop number 2, I can start from, for example, here. I can go this way, I can go this way, and that's a closed loop. Loop number 3, I can start from here and go all the way back here. So these 3 loops, and I color coded them so that it's easy for you to follow me. Step number 2, identify junctions. In here I have 1 junction and I have 2 junctions. Okay, now step number 3, select the current directions. Now remember, I'm going to put a lot of lines here under select. This is a choice. You can select the currents as I've done. I1 is clockwise, I2 is counterclockwise, I3 is clockwise, you can definitely select them the other way around if you want, and that's fine, as long as you keep the sign convention, the voltage drop, the voltage increase, correct. And the other point here is that once we get the answer, if the answer for I1, I2, or I3 is positive, that means that the direction of the current we selected is correct. However, if we get a negative number or a negative value for the current, then that means that our selection is wrong and we have to reverse the selection. All right. So let's start with loop number one, and then step number 4, apply Kirchhoff's rule for the each loop and the junction. Now you don't really have to do for each loop, because in this case I have 1, 2, 3. That means I only need 3 equations, and I have 1, 2, 3, 4, 5. So maybe, I mean, the best way, and I said this in class, is to combine. So if I take the first 2 loops and junction number 1, that should solve my problem. But let's go through all of them and then we'll see how we select. So for the voltage rule, for loop number 1, I'm going to start here. So 12, that's a voltage increase, and then a voltage drop because I'm going with the current along the direction of the current. So that's minus 50 I1, and then I'm going again with the current, direction of the current. So minus I3, this should be I3. For loop number 1, this should be I3. I'm sorry about that. Okay, all right, I3. And loop number 2 is this guy here. So if I start here and I'm going to go this way, so 24. Actually, let me see if later on it's fixed. So loop number, so 24, and then which way? Loop number 2. I'm going. Okay, now I'm going to go this way. So 24, and then plus, because I'm going against the direction of the current, that's plus, and 10 I3, and then again I'm going against the current, so that's 20 I2. So that's my second equation now. And loop number 3, I'm going to start here at 12 minus 50 I1, right? And then minus plus 20 I2, because I'm going against the current, and then going minus to negative, so that's again voltage increase plus 24. So the only mistake here is that this guy should be I3. Let's hope that it does not affect our calculations in the next calculations or the algebra. Okay, and then the junction rules. If I take this, it's I1 in I2, right? So I1 and then plus I2, these guys in, minus I3 out. Okay, so that's the, and similarly for junction 2, yeah, I only need one of them. So 2 of them in, these positive, and this is out negative, or I in is equal to I out. All right. So now I have 3 loops. I still did not correct that. It should be I3, and yeah, still not correct. So that means my solutions will be not right. Okay, so junction 1 will be this, and yeah, so this will not work out. I have to fix this now. All right, so that means you have to, all of this solution now I've suggested, because we made the mistake here for loop number 1. It should be here minus 10I3. Okay, so that means the solutions that I've done here is not accurate, the values, and you have to go and solve them. And maybe I should look at that and give you next time in the class what the solution is. All right, see what a simple mistake can do for you. All right, it's not intended, by the way, it's a real mistake. All right. Okay, so if we, if we take these wrong numbers, then so this one here is negative. The value for I2 is negative, which means what? Which means that the value that or the direction we selected is opposite to what it should be. And similarly for this one, if these numbers were correct. But remember, we have a problem here, and then we have to, all of these solutions have to be re-examined. And I'll give you, as I said, I promise I'll give you the answers in the class, inshallah, just to check your answers. All right, another example here. I have the same thing. I have 2 batteries, or similar. I have 2 batteries, and okay, and then all the resistors are all 4 ohms, okay, and I want to find the current I1, I2, I3, magnitude and direction. So if you look at the junction point here, the sum of the currents in, which is I1 plus I3, is equal to the current out, which is I2. Let's hope these are correct. And then if I take loop 1, 10 minus 4I1, and then plus 4I3. This is correct. 4I3 is equal to 0. And then this loop here, I'm going to start, I'm going this way. So 5 plus, I'm going against this guy. So my motion is this way, opposite to what I chose here. So let me just correct that. So the motion is this way. Okay. So I'm going against the current, so that means it's plus. And again here against the current is plus. So I have 3 equations and 3 unknowns. I can easily solve them. And when I solve these, that's what I got for this, except now again there is a mistake here, I2, I2. So I don't know which one of them is I2. That's a problem of cutting and pasting out. All right, that's all I have, with the exception of the few minor algebra mistakes, which I'll fix them. I'll show you, I'll give you the answers in class. But other than that, I think this is all. Please practice these. Maybe these mistakes will help you or will challenge you to find what the correct answers are. And thank you very much. Good luck to all.